Part C uses the same setup as parts A and B and asks us to design an amplifier with the transfer function given in the following image. So using this image, we can calculate the gain, the lower corner frequency, and the upper corner frequency. So the gain is 20 dB, and we want to convert that to a natural number, so that's 10 to the 20, that's the 20 from above, over 20, which equals 10. And then the lower corner frequency is 100 Hertz, and the upper corner frequency is 10 kilohertz. So now we want to calculate the capacitors that will give us the lower and upper corner frequencies that we're looking for. So the corner frequency equation is 1 over 2 pi R Thevenin times C. And for this problem, we will use the solution from part B because it already has a gain of 10, and that gain of 10 is what we're looking for. So for the lower corner frequency, we will plug in 100 equals 1 over 2 pi times R Thevenin. Now we need to calculate R Thevenin. And R Thevenin is looking into here for the input side for the lower corner frequency. So that's going to be Rs, which is 50, plus the parallel combination of R1, R2, and the input into the amplifier. The input into the amplifier we can get from our handy-dandy BJT amplifier equation sheet, and that will be this one because we have an RE. So this is R1 in parallel with R2 in parallel with R pi plus beta plus 1 times RE. Now, if we remember from part A, we had these conditions that we made. RC is much, much smaller than R naught. RC is much, much smaller than 1 meg. R pi is much, much smaller than R1. R pi is much, much smaller than R2. And R pi is much, much larger than 50. Now, because R pi is at least 10 times smaller than R1 and R2, because of the conditions that we set, we can neglect R1 and R2 because this is a parallel combination. Because this is R pi plus some other stuff, which makes it even larger. And then now we have R pi plus 50, and because R pi is much, much larger than 50, and this is a series combination between R pi and 50, we can also neglect 50. So now we can calculate this for R Thevenin. So R Thevenin equals R pi, and R pi is Vt over Ib, which is also beta Vt over Ic, because Ic equals beta Ib. So that equals 0.026 times beta, which is 300, over Ic, which we calculated to be 5 milliamps, but then we made a few changes to our equation, so let's just make sure. We're now at 4.1 milliamps, so that's pretty close to the same, so 0.004, and that will give us 1950. So we'll plug that back. Actually, let's go back to the corner frequency equation that we already started. So that's going to be 1950 plus beta plus 1, so that's going to be 301, times RE, and RE is 88, times C. So solving that for C, we call this C1, the lower corner frequency, we get 56 nanofarads. And then for our upper corner frequency, it's the same equation, so it's 10K equals 1 over 2 pi times R Thevenin, which is different in this equation, or is different for our app, because we're now looking into the amplifier from here. So we get RL in parallel with RC in parallel with the resistance that we see looking into the amplifier from the collector. We can get that from our handy-dandy equation sheet as well. That's going to be this one, because we still have an RE. So that's that equation, which is very long. However, we want to notice that that equation is a bunch of stuff plus R naught. So that's RL in parallel with RC in parallel with a bunch of stuff that includes R naught. Now because we have these conditions up here, that RC is much smaller than R naught, and it's much smaller than 1 meg, we can neglect all of this stuff that's plus R naught, because it has an R naught, and that will just make R naught larger when we add other stuff to it. And then RL is the 1 meg value. So since we have a parallel combination, RC is the dominant resistor because it's the smallest, and that's all that we have left for our R Thevenin. And then we also have to take this whole thing and multiply it by C, and so we're going to call this C2, and when we solve for that, we get 16 nanofarads. So now we'll jump over to LT Spice and plug in those values. So we'll change R1 to 56 nano, and then we will add change C1 to 56 nano, set C2 to 16 nano, and then we will do an AC analysis in order to check that our corner frequencies are what we want them to be. So we need to start below our lower corner frequency and go to something above our higher upper corner frequency. Remember to set the AC voltage source as the reference for the AC analysis. And then we'll measure V out. And our point where we're 3 dB down is 105 hertz, which is within 10% of 100 hertz. So we're good there. And then up here at 10.23 kilohertz is our upper corner frequency. Here we're 3 dB down again. And that's also within 10%, so we're good to go. So that is our solution for part C.